Hi, everyone. As Dan just said, my name's Steve Bronder, and we'll be talking today about automatic differentiation. Just some background, I'm a software engineer here at CCM. Most of my background is C++, and I only have a master's, but it's in statistics. For the last, I guess, 7 or 8 years, a lot of my work has been around the automatic differentiation framework that backs the Stan language, mostly a C++ math library. And our goals today are just laid out here. We're going to talk about what's automatic differentiation, why should you care about it, what's an expression graph, which is essentially the graphic that we use to represent automatic differentiation. And we'll be talking about the two main styles that automatic differentiation is actually implemented in a computer. And then we're talking about a handful of different automatic differentiation packages and saying, well, like, here's their trade-offs and benefits. But what is automatic differentiation in general? It's a computational technique to evaluate partial derivatives of a program. That's it. If I have a program with numeric inputs and numeric outputs, the goal of automatic differentiation is to be able to get back partial derivatives of my inputs. And this particular picture, I just asked Microsoft's DALL-E 3, hey, give me a physical representation of automatic differentiation in a classic Renaissance style, and that's very pretty. It has nothing to do with automatic differentiation, to be clear, but it is nice looking. But why use automatic differentiation, right? Well, like, you just need derivatives for a lot of the things that we use. A lot of gradient-based solvers and optimizers now are becoming like the main, normal stuff to use. This is just like a simple Newton-Raphson method we have in the equation up here as an example. But you can think of like Hamiltonian Monte Carlo, BFGS, stochastic gradient descent. These are all things where you need gradients at some level. And you have a few choices at that point. You can choose to just write out your gradients by hand. You could do simple finite difference techniques. Symbolic differentiation is also nice in some cases. Spectral differentiation if you have nice oscillating equations. And the most general one that I'm going to argue and the one that you should look to do is automatic differentiation. Automatic differentiation is nice because it's faster than finite difference, and it's more flexible than symbolic differentiation. When I say it's faster than finite difference for reverse mode, normally with finite difference, you have to just do one input parameter at a time, getting its individual gradient. Reverse mode automatic differentiation, you can get all of the gradients with one sweep, which is quite nice. And symbolic differentiation has a lot of catches. Like, for instance, like, you can't do like additional while loops, usually in symbolic differentiation. But yeah, so automatic differentiation allows for unknown length while and for loops at compile time. It is also accurate to floating point precision, so you don't have to worry about like what is the tolerance level I need for your given program, as much as relative to like finite difference. And let's see what else. So the one thing here is that it sounds like it's bad, but it's actually quite nice. Reverse mode automatic differentiation, in terms of like complexity or speed to do it relative to your original function, it's about 4 times as slow. But when you think of like 100,000 inputs with like finite difference, like, that's very, very slow. So only having 4x as slow is actually quite nice. But I only have 4 slides that have math. I'm not a huge math person. If I mess up any of the math, don't yell at me, my bad. But we just have a really simple function here, right? We have x0 and x1. We're doing a log times x1 plus sine of x0 to get back a scalar z. And if we wanted like the gradients of x0 and x1, or the partial derivatives of x0 and x1, that would just be our Jacobian, which is just in this case a single row vector. And we say, well, like, if I had to get a pen and a piece of paper and actually calculate the partial with respect to x0 and the partial with respect to x1, I would just take this equation and just keep applying the chain rule, probably going through until I finally got my end result of like x0 and x1's partial derivative. And we can kind of take that concept and just put it into a computer. Lot of words in this slide. But we can let v sub k be part of a sequence of intermediate expressions for the input x, or for the input x and output z. You can kind of think of this as that, like, if we want to apply the chain rule, we have to take a larger expression and break it down into smaller intermediate representations. And that's what we're doing here, where we set, for instance, like V aught just be a load of X aught and V1 being a load of X1. And we're going to let VK bar be the partial gradient of the kth intermediate step. If we write out all of these intermediate steps, we can just do the chain rule for each of those intermediate steps and do a backwards accumulation to actually get back the partial gradient or partial derivative. And this is just kind of an example here where starting with these loads, just doing loading X aught into V aught, loading X1 into V1. We then can just do log of V aught to get back our intermediate expression X2, sine of V aught to get V3. Then we do the multiply the two intermediates there for V4, and then add those two intermediates again for V5. We'll go through an expression graph that actually does the backwards derivatives to see what this looks like. But in math, we're essentially doing an accumulation of all of our partials of our current step with respect to its child step times our current step's adjoint. But yeah, this is just kind of like the, I guess, more formally definition, but just of what we talked about. To get the full Jacobian back, you can just use the chain rule to differentiate from each output to each input. We're going to be focusing on this particular case where we just have a row vector Jacobian, i.e. like we have a scalar output. The reason for that is because if you think of like most optimization algorithms and like most we tend to have a single scalar output that we are then like optimizing over, or like for our objective function. But automatic differentiation can work with like if you have multiple outputs, that's fine. And we can also do more than just Jacobians. We could do Hessians or like higher order partials if we wanted to. In this particular talk, I'm just going to be talking about gradients, just because I don't have enough time to talk about all the different schemes. But essentially, going back to 2 slides ago, we just need to break down these intermediate steps, know the gradients for each intermediate step, and do a reverse pass accumulation over all of those intermediate steps. And that's kind of what we're saying here. Like we did a lot of cool math, but when you actually put this into a computer, what we need to do is have a forward pass where we're literally just calculating the value of the function f, putting it into z. And then we need a reverse pass where we have a chain function given x or z, x aught, and x1 that can compute the partial with respect to x aught times z's gradient, and the partial with respect to x1 times z's gradient as well. That's just the adjoint. We just call it the adjoint Jacobian update for x aught and x1. When we this is like a very weird and nasty way to keep track of intermediate representations. So usually we use a thing called an expression graph whenever we want to show like what is automatic differentiation doing, like in terms of like dependencies. The expression graph is just going to be a dependency graph of intermediate computations. We'll go through a full example doing a forward pass and the full reverse pass, showing how the adjoint Jacobian actually works on the updates. Has anyone seen pictures of this before? If you can raise your hand, people know what this is? Totally. I always got super confused by these. They also like tend to flip them upside down, so you have your inputs at the bottom. I didn't like that, so I didn't do that. But we're just going to work through actually like how do you like this. I feel like there's a lot of implied knowledge when you look at these graphs, and so I'm just going to like work through piece by piece, like literally how you build this up and then think about it. Just to start, we're going to do that load operation we talked about before. Oh, and our function here is just the same function we had before with x and y instead. I didn't like having to say x aught and x1 all the time. But yeah, here we just do a load of x and a load of y, and that just gives us v1 and v2. We do a log transform on v2. That gives us our node for v3. Same thing for sine. That gives us v4. Then we do v1 times v3 to give us our node v5. And then we just do v5 plus v4 to get our node v6. So this is our forward pass traversal in automatic differentiation. That's all it is. You can think about working with arithmetic values here. The cool part for autodiff is whenever we're talking about doing these partials. Because we've broken this down into much smaller things, or into like much smaller expressions, the actual like we just need like calc 1 level style like calculus to like be able to get the full adjoint of our entire full expression, or sorry, partial derivative of our full expression. And you can see here, this is just like basic Calc 1, x times y. The gradient with respect to x is y, gradient, or partial with respect to x is y, partial with respect to, oh, sorry, I'm getting confused. Partial with respect to x is y, partial with respect to y is x. But these are just simple rules. And we're going to go, starting from the very bottom, we're going to be applying this top level equation where we have the partial of the I plus the gradient of our current intermediate steps is equal to the gradient of our child intermediate step divided by the, or with respect to our current intermediate step times the gradient of our child intermediate step, I plus 1. So just going back to this graph, we're starting with the very bottom node. We're going to do the partial of V6 just with respect to itself because it is the last node. There's nothing else that it depends on. And you just get back a gradient of 1. For V5's gradient here, we're going to do the partial of V6 with respect to V5. That's just addition, easy peasy. 1. V6's gradient is also 1, so 1 times 1 is 1. That one's easy. This is another easy one because we're just still going based off of the partial of V4 with respect to doing partial of V6 with respect to V4. And that's just 1 again. It starts getting kind of interesting here where the partial of V5 with respect to V3 just gives us V1. But again, the actual adjoint accumulation is still just 1 here. So we just multiply it through and it drops off. And then here in V2, we have 2 child nodes. And so what we want to do is do the partial of V3 with respect to V2. And that'll just be 1 over V2 and then times V1 because that's V3's adjoint there. And then we also do the right child node as well. We have partial of V4 with respect to V2. And that's just going to be cosine V2. V4's adjoint is 1, so it drops. And so we get our full partial derivative equation there. One other thing that's very nice is that as we go in our program up this expression graph, we've already calculated V5 here, V5's adjoint. So we actually can just store that information. And whenever we do this full sweep, we won't have to recalculate this. But yeah, we can see here that the partial of, so V1's partial derivative or adjoint here is just the derivative of V5 with respect to V1 times the adjoint of V5. And that's just going to be V3. And this is kind of a nice example because if you like just work it out by hand, like the partial of this equation with respect to y is just log of x. And like the same thing is true for doing the partial with respect to x. So like it's just nice you can like hand verify that like this is like how it all works. But yeah, again, like how do we take this expression graph and just put it into a computer? Well, like again, like we just need like we need some form or way to think about this expression graph where we just do a forward pass and a reverse pass, accumulating these adjoints with respect to each of their partials. In a computer, you could actually like go and have a big linked list structure and actually write out your full expression graph like this, keeping track of things. We tend to do a topological sort of the expression graph, where a topological sort just means that if you have like a graph or tree, you can lay it down linearly where each of its parent nodes precedes the child nodes. That's what we're doing here. We can see that we're just laying this linearly for the forward pass, going this way with all its dependencies. And we're going for the reverse pass, just flipping all of the dependencies. And this is kind of, as we get to the programming side of it, this is how we're going to lay out things in memory. We're just going to essentially have a big vector, or so like in one scheme, we will just have essentially a big vector that we'll be adding to constantly to keep track of our expression graph. But when we do this, when we write something and we need to keep track of this reverse pass, which is like the hardest part, just keeping track of where we've been, like the size of our expression tree, there's 2 main ways. to do that. We can do what's called source code transformation, where we literally would take our program and write a transpiler that would then write out that full forward pass and that full reverse pass just with arrow, sorry, with floating point, and you'd get back a result of like the derivative that way. This is cool because it's like super fast. If you can like unroll everything in your expression graph to just essentially like hard code the forward and reverse pass, like that's sick. It's gonna be super fast. This is also like really hard to implement. To my knowledge, there's only really one large package. Well, there's one package that does it right now that we'll talk about at the end of the talk. That it's pretty cool how this one works, but it's pretty restrictive in what you're actually able to do. For instance, like this thing does require, when you do source code transformation, it does require like full knowledge of the size of the expression graph at compile time. So again, like things like conditional loops just like don't work. On the flip side of that, we have object-oriented operator overloading as a scheme for setting up automatic differentiation, where we literally just treat the nodes in the expression graph as if they are like structs or classes, just small objects. Those objects will store the function for the forward pass, a function for the reverse pass, and any additional information that we need for the reverse pass as well. This is way easier to implement, which is nice, and it's extremely flexible. The downside is that there's way less optimization opportunities. And I'll say that for most newer AD packages, they are doing a scheme that combines both of these ideas, where they're taking like the log and sine nodes, and then at runtime, they're running usually a JIT compiler to combine both of those nodes together into one large node. But most of the choices that we pick here are kind of dependent on what we want to do, what we as like automatic differentiation software developers like want our package to do. The fastest scheme is to have what we call a static graph, or it means that when we compile our program, we know exactly how large our expression graph is going to be. But that has a lot of constraints. Like for instance, in a compiled language, you have to then say, I compile time, I know exactly how large all my matrices will be. That's not super fun for like things you want to run multiple times. There's also things like, again, like not allowing conditionals. And kind of a weird thing, a lot of automatic differentiation packages, like if you've used like PyTorch or JAX or TensorFlow, they like don't allow you to make a matrix and then reassign to subsets of that matrix. And it's oftentimes because they're doing a JIT scheme or a like semi-static graph scheme that is extremely hard to do reassignment in. Stan does allow for this, but like the guy who figured it out, I like could not read his. We had to sit down and talk for like 2 hours so so he could read out his code and I could understand how the heck it worked, because it was really impressive. I now kind of get it. But then, yeah, kind of the other question as like a developer when you're like working on an auto differentiation or automatic differentiation package is just how much time do I literally have? The static graph stuff just takes a lot of time to write. And we'll kind of show an example here. So this is an example of this doing a source code transformation. I didn't actually write a transpiler because like that would be a little bit extra. I didn't want to have to go do that. But you can see that we have just writing out z is equal to log of x times y plus sine of x. If we handed this to our transpiler to actually do the automatic differentiation for us, or write out the code to do automatic differentiation, the first thing it would do is literally what we did in our expression graph. It would just write out v1 through v6, and then just assign our final value of to get back z. It would then go through and just start writing out the reverse pass as well. So you can see it starts at dv6, just setting it to 1, going down through dv543, doing exactly what we did essentially. Oh, I have a typo on one of these. You can ignore that though. This is just an example. And then finally, till we get back to like dv2 and dv1, right, where we're just doing like our full accumulation for all of our past derivative values. And like that's cool. Like it's really like you're working with all floating point. Like this is super fast. But like again, like I just can't do this. And like there's just a lot of times where having something like this, or even a for loop that'll end after a certain period of time, is like really nice to have. And source code transformation just can't allow that. In the object-oriented approach, what we usually do is if we go back to our topological sort of the expression graph, again, we're just going to treat each of these as like little classes and structs. So we're going to be, as we go through these, just making a little class that represents log, a log function, keeping our forward and reverse pass information on it, and then just putting it into a vector, essentially, just keeps track of the expression graphs linearly. It's super flexible. We're going to see in just a minute. And the nodes, and I won't talk about this too much. I might if I have time, but often the nodes of the expression graph can still be collapsed in the schema. So can everyone see this? Is this text big enough? How's that? Cool. Okay, so I'm going to start. So this is if no one has used Godbolt before, it is just a online C++ compiler that also lets you kind of execute some simple programs. And I mostly use it to like read assembly stuff. That's what it's like mainly built for. But here I'm just using it because like in like this is what in 297 lines I wrote like a pretty much full automatic differentiation package. Like essentially there's only a handful of functions in it, but all of the nuts and bolts are here, and I'm going to post this online as well so people can play with it. And this is also, I'd say, like 90% correctish with like literally like how Stan's math library is written in terms of like the implementation.
Which library did you say? This is like a template library for C++ that you're using.
Oh,
and
sorry.
Including somewhere above that code. Is that kind of what's happening?
No. This is all written as one single example in Godbolt. So it's 300 lines, and it does all of this stuff for us.
Right. And which is the library that, or there is no library. You built your own
this
set
is the
of
library.
Objects that do all of the, like this grad thing and the var, all of those things. They're all in this code.
It's all here. It's a standalone example for automatic differentiation.
Cool.
Yeah, I'm going to go through. How much time do I have? Oh, I have plenty of time. Yeah, I'm going to really dig into this. Cool. Yeah. No, so we're not going to go too crazy. But yeah, so like essentially we have a var type, right? X and Y. We're going to use it to like set up our initial problem. Running the exact same function again. We're just saying z equal to log of x times y plus sine of x. We call this gradient function here z, or giving it z. That's like the end of our expression tree, right? Or expression graph, excuse me. Just a bunch of pretty printing here. Don't worry about this guy right now. We'll talk about that in a minute. But you can see on the right-hand side, we're doing exactly like before. X and Y are associated with V1 and V2. We're doing a sine function, and then we're doing log, then we're doing multiply, then we're doing add, building our expression graph just like in our little expression graph picture we saw earlier. And you can also look and see that it goes through, once we call grad here, it starts the reverse mode, going from V6, doing the add operation, doing that adjoint accumulation, doing the multiply at V5, log at V4, sine at V3, and then finally getting back our full adjoints for V2 and V1. We just print those out using the value and adjoint functions. Oh, excuse me. And then we have another example here, essentially exact same thing, but kind of showing like why like the dynamic graph and object-oriented approach is nice. Same thing, x, y, same function. And I have a little while loop here. I just say, hey, while the value of z is less than 10, I want to do an accumulation into z of the exact same function over and over again. And then once I go once the z's value goes past 10, just stop. And for this, that's totally cool. We can do that. We go through then essentially calling grad and then releasing the memory that we were using. But you can see here, while we do our while loop, it just keeps building up the expression graph deeper and deeper and deeper until z goes past 10. We call grad again, starting from the very bottom. It just follows everything up until we get to our final V2 and V1 for our full adjoint accumulation. So like, this is super flexible and nice. Like if you can think of like, whenever Stan like first started, for instance, whenever we had someone asked for an ODE solver to be plugged into Stan, And we literally just used the Boost C++ library's ODE solver passing in our var type. And that's like horrifically expensive, right? Because like for every single loop of our ODE solver in the while loop they use, we're building up this humongous expression tree. But it did allow us to like very simply like just have access to an ODE solver. But yeah, so we'll go a bit higher up in the code now, start talking about some stuff. So, yo. No, we do not. No, it's super new. Particular, someone very cool went through and did a bunch of implicit function theory stuff to make our ODEs very fast.
On that, does that mean you write down the adjoint ODE and send that to the solver along with the original variables?
Yeah.
Or something. You've got to solve it backwards then.
Something like that. Charles is the guy to ask about this. But it's not as slow anymore.
The guy who asked a question?
Yes.
All right.
I love having a wand up here. Sorry, I keep playing with it. It's super cool. Yeah. But essentially, like, so we called the sign. Oh, I can't. This is silly. I can't. I love it though. It's really cool. But yeah, so we have our sign function here, taking in a var, right? We have a function called makeVar that takes two particular inputs, right? It has the value of the forward pass, which is just taking x's value, doing the sign transform on it, and then it has this anonymous functor here. For people who don't do C++, I'm just going to read this out. X here is just being captured. You can kind of think of this less as an anonymous function and much more of it as an anonymous class or struct. X gets captured here in these brackets. Our functor's signature is just taking in a var that is named ret. And then boom, just like in our expression graph earlier, we see STD and cosine. The adjoint of x is being accumulated by the value of x transformed by cosine times the adjoint of that return value, which is like essentially the output. And then that print statement is just to do pretty printing. But that's kind of nice. Like, and kind of succinctly, like we can write like a lot of functions quickly. Multiplication, same thing. You just do the value. We call this makeVar function to make the output. We do the forward mode, which is just the value of the left-hand side and right-hand side multiplied together. We capture the left-hand side and right-hand side here for our lambda. The functor or the signature for that lambda just has a var as the input. And then we do the adjoint accumulation, same as always. And that's really it. All these kind of work like that. Working through a bit more of the back end, this actual makeVar function that we're using in all of these, this gets a little weird, but it's fun. So template, don't worry about that. It just essentially means that like we have an anonymous, that anonymous class or lambda. This makeVar function just returns back a new var, which actually is going to hold a pointer to this lambda var impl thing that also gets that lambda, and we pass things down. That lambda var impl just literally holds our actual functor here. Just holds our actual lambda here. And there's another level of indirection here through inheritance, which is kind of messy, but essentially var impl is our actual scheme to like hold the value and adjoint we'll be using. We pass val into var impl. Lambda here just gets moved over. This reverse function is what we're actually going to be using whenever we call our reverse pass. So you can see down here, oh, sorry, I skipped over the grad function, which is important. The grad function here just takes in z. It assumes that it's the bottom of the expression tree. It sets its adjoint, expression graph. It sets the adjoint of z equal to 1 because it's just the partial with respect to itself. And then we're going to be looping over this reverse stack, which is what we use to actually keep track of like all of our expression graph for our given section of the program. We start from the very bottom of the expression graph, working our way up, just calling this reverse function over and over and over again, which is like the chain, which is essentially the chain function. The reverse function calls the chain rule for that intermediary expression.
What's the point of these lambdas? Is that if, I mean, I find that page incomprehensible, but
Totally. So
Is that if the user defines Lambda functions? Is that what that's to handle?
yeah, so essentially I wrote this out just so I was really worried about using like any C++y stuff because I like wanted to make sure it was accessible for everyone. But whenever I first wrote this out and showed it to Bob and Brian, it was like 800 or 900 lines long. Because like essentially like if we don't have this lambda thing, then I do have to have a struct like add, right? And like then I'm going to have to store the var left-hand side, var right-hand side, and then
So for every
yeah,
math operation would have to have its own struct. Is that it?
yeah, essentially like so you'd have
So
something
it's
like
some
this.
kind of meta programming, so you don't have to write that.
Exactly.
Okay.
Yeah, but that's the only reason why, because once you add up all these, it just ends up being a lot of lines of code. The lambda just makes it a little bit simpler yeah, it
Makes your brain hurt.
yes, yeah. If you're not used to it, it certainly can be really clunky. But if you're used to C++ or if you're used to like using anonymous functions in Python, like I think they kind of make sense. Um, yeah, this is essentially like the last level of like this is like the weirdest indirection. This is the only template I think I have actually in this example. These print var functions just we're using for pretty printing, so I don't worry about those. These adjoint and value functions are just grabbing out the actual doubles we use for the value and the adjoint. And this is like the real meat and potatoes of Stan, actually. Like this is this is essentially like nearly what we have in Stan math C++ library. We have a var struct, which we actually use as our underlying scalar type. It holds a pointer to the actual var implementation. We can just create those var implementations here by passing in a double to this constructor. And like you'll notice that I'm doing these news. For people who do C++ and C, you'll see I'm doing news and not doing any deletes. That's on purpose. I'm not tracking deletes. And that's good. No, like you think I'm joking. It's really cool. We're going to see in a minute, I promise. This is the actual var impl. This is like the thing that actually stores stuff. We have our doubles for values and adjoints. We have this virtual function called reverse that actually like is what we use to then go call our chain rule. The main thing here, so for Python people, you can think of this as like a like inheritance essentially. Like if you declare a function in C++ virtual, in Python that would just be like you have a child, you have a parent class for your child class, and you're going to overwrite this function in your child class. But having this reverse function or this reverse function be virtual is what allows that lambda to be called in lambda var impl whenever we call reverse, and lets us have this kind of succinct style of writing automatic differentiation stuff. You also see that I'm overwriting operator new here. And I'm saying, hey, actually, like I just have an arena allocator. What happens here usually is that like when we're doing automatic differentiation, we're doing it in sort of like in something like Hamiltonian Monte Carlo or stochastic gradient descent, where we have just a giant while loop or for loop we're running over and over and over again. And if we didn't overwrite operator new here, what we would do is each iteration, we would be building up a bunch of memory. At the end of the iteration, we would just clean that memory up, give it back to the system. And we don't want to do that because asking for memory and over is just really slow. And like, I don't know, no one likes it. And so like what we can do instead is when we do our while loop after the first iteration, that's a pretty good approximation of how much memory we're going to need every time we run that while loop. So what we can do is every time we make a new var impl, we're going to put it on the actual arena of memory that we are allocating over the iteration of the while loop. At the end of the while loop, we will call this release mem function. And all it does, so we're going to talk about the reverse stack thing in a minute, but all the arena does in this function is just recover everything. And that doesn't mean delete it. It just means I have a literal integer that's keeping track of all of the memory I've allocated. And I'm just going to set that integer back to 0. And so in the next while loop, whenever I ask for memory from that arena, it's just going to give me memory that I've already allocated. If you do like just general while loops in your programs often, like I super recommend having like a arena memory allocator. It's like super nice. Very cute tool.
So Steve, this is basically you have your own heap in house.
Yeah, exactly. Yeah. And this also does another sneaky thing. We have a oh, sorry. So this reverse stack here and this arena are also static globals in this example. You could do something better if you wanted to. I think this is fine. The reverse stack here is just a vector that, again, stores our var impl. Var impl stores our reverse function that actually lets us call the chain rule, going back through all of our intermediate expressions. Which feels like a lot, but honestly, like it's a very nice and concise way to do autodiff. Reverse mode autodiff. You can see here, arena. I'm not going to go over the actual arena allocator. I think it's out of the scope of this talk. You can look. It's 160 lines, so it's not that bad looking. And then the actual reverse stack is just an STD vector of pointers to those var implementations. But yeah, that is kind of like the whole. If you can understand these 300 lines of code, you will essentially understand like how all of Stan math works and how most autodiff libraries actually operate, which is pretty nice. But yeah, that's all I got for respect to object-oriented operator overloading. It's the one, oh, I don't care about document properties. It's the one that I just am way more knowledgeable of, so that's kind of why I wanted to talk about it more. I've never written a transpiler for automatic differentiation, though I think it's a really fun technique for doing autodiff.
Can I ask again? So what's the take home for this is either write your own like you did or use yours, or is yours like a toy version of something that's out there, like a vector class library or some other library that we just use? I mean, you're gonna go through that now? Like,
yes.
What should we use?
Totally. Thank you so much. Yeah, let me
clarify.
Write
that lambda function.
Do not use the code I just showed you in any type of actual system. That would be super bad. I'm sure that it's like not going to crash, but like it's just like not great. There's a lot of like super good libraries for automatic differentiation that exist. Like that is like what you should be using. We're going to go over a bunch of those in a minute and their pros and cons, or not their pros and cons, but like what they kind of believe in as they're building their system. Am I going to talk about this? I'll come back to this later.
Yeah. Are you going to talk about like if there's ever a time we should do forward mode automatic differentiation, or should we always do reverse mode?
So if you want just gradients, I would just always do reverse mode. I don't think I'd have time in the scope of this talk to talk about forward mode, but totally. Forward mode automatic differentiation is just another scheme where the math's a little different, but essentially like you are taking the derivative of each input with respect to the outputs. The reason specifically why I said, oh, we're only going to focus on the case where we have many, many inputs and a single output is because generally that's what reverse mode AD is good for. You're just doing one sweep from a single input to a single output. If you have 6 outputs, you do have to run reverse mode for each one of those outputs, starting from the bottom, going up the bottom of each output, going all the way up to the top in your expression graph. Forward mode, if you use really forward mode autodiff, is the case where if you have very few inputs and very many outputs, that's what you want to be looking for forward mode automatic differentiation. But in this scope, we won't talk about it too much. You also use it a lot for higher order autodiff. Yeah. One sort of fun thing. Yeah, let's actually talk about this. So we did talk about, right, like, so this is sort of a pseudocode here. But a big question in automatic differentiation libraries is how do you represent matrices? Because there's a nice and flexible way, and there is a kind of harder way that's much, much faster. We tend to call those arrays of structs or struct of arrays. You can see here in our example, we have a simple, like, this is just a pseudocode of like that var type I showed you earlier. And if we want to have an actual matrix of those vars, we just create a raw array of those var types and then just put those inside of a matrix class. This is nice because it's simple. If we want to be doing things like assignment, well, the main thing that's really nice about this scheme is that if all of your underlying scalars are vars and all of your vars can work anywhere where a floating point can work, a ton of algorithms just instantly open up to you. For instance, again, whenever Stan first started, we didn't have an actual reverse mode for Cholesky decompositions. We just literally were using the C++ package eigen, using our internal var type as the scalar, and then just calling the Cholesky function, which would then run the Cholesky algorithm. And then it just runs whenever you want the partial derivative, you just, whenever you want to go up on the reverse pass, you're just going and auto diffing through the Cholesky algorithm. Again, not super fast, but lets you like get a lot of stuff out very quickly in terms of the algorithms you can use. On the flip side, you could say, well, look, like normally whenever I'm doing matrix stuff, like a matrix multiplication, I either want all of the values at one point in time, or I want all the adjoints at one point in time. I don't really need both of them sitting next to each other. So what we can do instead is split out the values and adjoints into two separate arrays. And this is super nice because then we can treat that entire matrix as a single node in our expression graph. And that allows us to do, that collapses a ton of the expression graph. And also having these be contiguous arrays allows us to do much faster things in our CPUs, because our CPUs normally can do single expression, multiple data operations, which just means like, instead of doing like one multiply at once, it can do like 4 multiplies at once. A big condition to be able to do those single instruction multiple data operations is that the memory that you're working on has to be contiguous, and it can only be contiguous normally if it's inside of an array. The bad side of splitting this out into a struct of arrays is that it is essentially its own style of node where every single operation we need to explicitly write out. We cannot use this nice property of defining things for scalars and having them work for matrices. We have to actually write out like the matrix multiplication adjoint, which like is for matrix multiplication is simple. When you start doing decompositions, it starts getting very hard. But a lot of the autodiff libraries we're going to look at in just a second. Oh, sorry, go ahead.
Just a little briefly, you mentioned that the var matrix can collapse some of the expressions in our computation graph.
Mm-hmm.
Could you explain why we're able to collapse them?
Sure. So if we go back to our original expression graph, just imagine that like X here is a matrix, and we're using that matrix with the inner scalar of var. So now we're going to be operating on X odd, X1, X2, X3, right? And each of those nodes is then going to have its own log node. And then each of those nodes, each of those like X odd, X1, X2 is going to have its own sign node, right? And that'll like make our expression graph a lot larger. If we instead use the matrix, if we instead do the matrix scheme where we have the values and adjoints just as like 2 arrays of doubles, those X aughts, whatever, all just collapse into the big matrix X. Now we just have a single log node where we're actually doing the log, we're doing an unary function on that matrix of doing log. But essentially it just lets us treat like the entire matrix as one single thing, as one single object, instead of a composition of many smaller objects. Does that make sense?
Yeah.
Cool. But yeah, that's essentially the pros and cons of choosing the array of structs, the first one, or the struct of arrays, which is the second one. The array of structures can be way more flexible for your end users and yourself as a developer, while the struct of arrays is hard, but is way faster. And most like PyTorch, JAX all do this struct of arrays approach. We're now going to talk about a few AD packages or automatic differentiation packages. I'm going to be kind of grading them, not grading them. I'm going to be kind of thinking about them in terms of how flexible they are, how efficient they are, and how good they are scaling. What I want to make clear here is flexibility. I just mean how easy is this to debug? If I do something bad, will you throw an exception and actually tell me that I'm wrong, or will you just continue running? Can I run conditional loops? And again, can I do matrix subset assignment? I think it's really weird that a lot of packages don't support that. I don't know if you're in R in Python, it seems very like, it's a thing that you should be allowed to do. Efficiency is just literally if I have a single GPU or CPU, how fast are you on that? Like it's small to medium-sized problems. Maybe you have like 200,000 parameters, no more than that. Scaling is going to be like if I have to manage like hundreds of clusters where I have a few hundred also GPUs, and like each node in my cluster will have like 8 GPUs. How does your automatic differentiation package manage there? This is sort of the graphic that of the ones that I'm gonna talk about. And like, I wanna make it clear, like this is very vibes and me based. Like this is, don't take a picture of this, put that down. I am not getting in trouble with Google because I put TensorFlow really by down here. But yeah, like essentially like, I like all of these. I think they're all very good. Whenever I have gone through and played with all of them, this is kind of how I think about them in terms of like, how much do they care about like the end user's time in terms of flexibility? How much do they care about the actual performance on a single CPU? And how much do they care about scaling up to many GPUs? Yeah, they're very cool. We're talking about each piece of these and kind of like, I'll say like, being far away from performance and scaling, PyTorch is number 2 to me. I really like PyTorch. They have like a very nice paradigm. They like they're like, no, like it's hard to write these models. We care about like user time. And I'm like, that's sick. I love that. But we're gonna go through and talk about each of these. In general, like, so some of these nowadays can actually flip between static and dynamic graph stuff. For instance, PyTorch now has a setting to make everything static graph, which is fine. TensorFlow and JAX. I think JAX now has a dynamic graph thing. You can turn off eager mode in TensorFlow as well. But by default, their regular thing is to be a static graph thing where they assume they know how big everything is going to be when you first execute your program. So just talking about each one of these. Stan, I like it. It's pretty cool. It's very flexible in terms of like what you can do. We throw exceptions. If you want while loops, we can do that. We allow matrix subsetting. And to my knowledge, and we get pinged about papers all the time, there's only one package I've ever seen that's actually faster than Stan Math, and that's a C++ package called FastAD. This guy, James Yang, is a PhD student at Stanford. One summer, he messaged like me and this guy Ben Bale saying, "Hey, like I wrote this little package over the summer. It seems to be way faster than Stan. Like, could you like look and see if I'm doing something wrong?" And I was like, "Oh no, like you're doing everything right, and you're a lot faster than Stan. What'd you do?" And like it was really good. It's just, but I don't have time to talk about it. And it's kind of, he just sort of write it like for fun, and then like forgot about it. And I was like, dude, like why don't you like keep doing this? Like it was cool. The other thing that's nice is that like Stan Math. So Stan Math is actual C++ library for automatic differentiation. It has a domain specific language that's very C-like on top of it. We do allow tuples now, thanks to Brian Ward, which is fantastic. But you have arrays, you have matrices, you have vectors, you have scalars. That's it. And it's also kind of one of the downsides, right? Like in Stan, at this high level language, we don't have things like dictionaries that you'd have in Python. For like some software engineering style developers, like that could be kind of an issue. We do not scale well, and we don't have any intentions to ever scale to things like terabytes of data. We are not the thing for doing deep learning models. Just absolutely bad idea. For us, for you guys, that's great. That's fine. Also, Stan's compiled. We have a backend of, we transpile our Stan native language, Stan domain specific language into C++. And when you're actually building out models, having to wait 30 or 45 seconds for your C++ to compile so you can run your slightly tweaked model, it's kind of annoying. But like, it is very fast. So when you have a project that takes like I've had models that take like a few weeks to actually run, and I actually do want to pay for that 30 to 45 seconds of compilation at that point, whenever I'm all good and done, ready to run my big model. We have extremely limited GPU support. At the math C++ library level, we actually have a lot of support, but it hasn't trickled up to the language yet. But hopefully this year, I think we're going to finish that. PyTorch. I said before, I think PyTorch is super cool. It has great multi-GPU support. They actually have exceptions. You can do conditional loops. They like right on their like front page of their README, they're like, hey, like debugging your model is like our first priority. Like that's the thing that like we care about. And like I like that a lot. I think that like it's important to care about user time. Lots of cool built-ins for your neural networks, and it's also like pretty extensible at the Python level, at least. Brian and Michael recently did an extension called PyTorch, FINU FFT. Is that how you pronounce it? FINU? FINUFT? Yeah. For the fast Fourier, was it normalized uniform fast Fourier transform? Non-uniform. Thank you. But yeah, so at the Python level, it's very extensible. The thing I don't like about it, honestly, is just that like I can't, again, like I can't do sub-assignment for matrices and vectors. I don't like that. The backend is also like super hard to, like I've like written and have read some like really nasty C++. I have like, I don't really, so there's parts of their backend that are actually C++ that is put into a JSON file as a text string. And yeah, no, like I'm not joking. And they use that for it's like you have to write it in a specific way so it can get read into their GPU stuff and their CPU stuff. And like, I don't know why. I'm sure they're people at Meta are very smart. Oh, this is also run by Meta. They're very smart people. I'm sure that they had some reason to have code written in a JSON file, but I don't, yeah, I just was like, I was gonna like contribute stuff. I was like, oh, that's cool. And I was like, no, I'm good. Like, I'm not doing that. TensorFlow. TensorFlow. No, I'm not gonna say anything mean. I'm not gonna say anything mean for real. If you like legit, like if you are a guy who has to care, if you're a guy or girl who has to care about like, hey, I have hundreds of GPUs across different nodes, and I have to really think very directly about how I'm sending data between those and aggregating them. Like TensorFlow is like the thing to use and the thing you should use. But it's really made for software engineers. It is not made for like scientists or people who want to do statistical modeling. So if you're not thinking about like the nuts and bolts of like how you are moving data around a large and complex system, then I don't recommend TensorFlow. It's all static, so you don't have things like conditional loops. You don't have sub-assignment to matrices and vectors, and you have no exceptions. I think Charles I was talking to previously who told me about how he was running an ODE solver in TensorFlow, and it just like doesn't fail. Like it doesn't tell you that you're wrong. It just keeps trying to go. About 6 years ago.
So it was
oh, go ahead.
both in TensorFlow and in JAX.
Yeah.
Yeah.
Google,
and
yeah.
I submitted an issue. So that, hey, the ODE is giving me the wrong result. It's not reporting that it's not converting. Like, yeah, it's not worth it to us to implement that error message.
Yeah. Oh yeah, yeah. So this is much more of a Google thing. They famously hate throwing any sort of exception. There was also like some weird points in there. I think their code is fixed now, but like 6 or 7 years ago, their Cholesky decomposition would take doubles and cast them down to floats because they thought it was faster. I like super don't recommend doing that. It was for sure. But like it's made for software engineers. Like if you're not a software engineer, like I don't recommend touching TensorFlow too much. I love JAX though. I think JAX is fantastic. It's built on Autograd, so Autograd was a C++ automatic differentiation library. The guy from Autograd got hired to Google, rewrote Autograd and worked with some guys with their XLA compiler to get like a very nice like Python automatic differentiation that like can give you like C++ like speeds. I think it's pretty well documented. I think it looks nice. I think you can kind of see what happens. It's extendable. I've had a lot of friends who there's a lot of schemes in JAX that will allow you to actually have like a black box version of a black box piece of your model, where then in the reverse pass you tell it like what is the adjoint for this particular thing. I think that's nice. And yeah, just being able to write Python and like, so sorry, JIT here for anyone who's not clear. So good. Does it?
It's just very well hidden and it's not very well documented, but
Oh, awesome. Okay, I will change the slide then. Good for them. Happy about that. It what? Oh, can you do while loops here? I was looking at their examples and they only had for each I statements. Oh,
You
interesting.
can do while
Okay.
loops, but sometimes grad fails and it doesn't tell you why through while loops. It's
So
gray
that
zone.
was when I was reading the docs online. That was like the foot gun step, is where like they have like technically you can have while loops, but then like it can fail.
Some of the features hidden in the source code in another repo, so that makes me like, why you need to like the good features are not well documented.
Oh, I don't love that. Good to know. Thank you. Yeah, I just glad this slide is totally wrong. Then maybe I don't like Jackson. I don't know. Yeah, famous. Google loves doing that. Absolutely. But yeah, I still think it's cool. And it's used a lot, and I think it's fun. I'm glad to know those things now. I was trying to look around, and I had a hard time finding those. And then enzyme.jl, this is the only Julia package I'm going to include, and it's not really actually a Julia thing. So Enzyme was a project by a guy at MIT who wanted to do source code transformation over in the LLVM part of the Clang compiler. So essentially, like going back to like if we go back to this original code, it was literally just trying to do this, where you would give it an original function and they would unrule everything for you to do autodiff directly in the compiler, which is cool because once the compiler knows that much information, it can do a lot of very neat things. Enzyme builds on top of that. Essentially, since Julia is built on top of LLVM, they're like, oh, well, like we should just use this for a main autodiff. And it's nice. It is really fast. The downsides of enzyme.jl is that there's only one maintainer. I think in like 2021, he was like, oh, I'm gonna like take a break for a year. And then like that was like it. There's like no pushes, no commits, no nothing. So like not super well maintained. It's only at 0.1. Oh, sorry, also to clarify for a second, enzyme.jl only has one maintainer. The actual enzyme in LLVM has a bunch of different maintainers through both Rust and the original LLM team. The Rust guy is also really interested in enzyme. But enzyme.jl is on 0.1 right now. So like if you build software on it, it is like not guaranteed to stay like not broken. And also a really weird thing is that like you have with Julia, the nice thing is that you have like a lot of different packages you can just throw into other packages and they tend to just work. The catch with enzyme.jl is that it's all static graph. It has to know exactly what it's doing. If your other package you're using does garbage collection or what's called dynamic dispatch in Julia, it will just fail. It will go badly, and that's not like that bad of a condition. I mean, like given what they're doing is super hard, and so like I think this is a really cool package. But yeah, there are like definitely some catches to it that are neat. But that is pretty much the end of my talk. I hope I went over and explained what automatic differentiation is and why you should care about it. I think we worked nicely through the expression graphs, and then we talked about how different automatic differentiation packages implement. And then I kind of gave you some takes and trade-offs on different automatic differentiation packages. But that's all I have to say. Thank you so much for your time.
Thanks so much, Steve, for a fantastic talk. Do we have any questions for Steve? Alex.
Sure. So at the very beginning, you made this great point that is kind of amazing thing that it's basically 3 or 4 times the number of flops, regardless of the problem and regardless of how many inputs, you get all of the derivatives in 3 or 4 times the number of flops.
Mm-hmm.
Does that translate to 3 or 4 times the runtime? When you say, you know, in the performance ones, let's say Stan or this fast AD or something, is your code going to run 3 or 4 times longer and that's it? You know, or like, does it depend on how much extra RAM it creates or something?
It's a great question. It doesn't often translate as well. So again, in the Cholesky decomposition example, I think the reverse pass is n cubed actually to calculate. It's very expensive to calculate the reverse pass of the Cholesky decomposition for the AD. I forget what the exact complexity is, but yeah. So while it's true that it is like only 4 times as many like operations flops, in terms of runtime, you still can end up with segments that are more expensive.
Then it has to be RAM. It's a memory movement or allocation or something.
Yeah.
Okay.
So in the case of non-commutative binary operators, I guess the expression graph wouldn't really be a graph because it matters the order. Does that ever happen? And is there a name for that type of graph?
Non-commutative binary operators.
Well, because then the order of the inputs matters, right?
yeah. Oh, I think it would kind of be, I think you could kind of splay that out as like, if you were in like C, right, you would have like a function for like the left-hand side operation, the function for the right-hand side operation. I don't know what the word non-commutative binary operators means. Yeah, we can talk after.
I think a good example might be matrix multiply.
Yeah.
Oh,
Or
Um,
Right?
or
'Cause you
division.
can't, BA is not AB, so you'd have
Oh,
to
got
know
it.
which one.
Sorry.
Yeah.
How would that work? Going back to our graph, that would be fine. What we would have for like non-commutative binary operators is that you just have the partial when you, so like the matrix multiplication is kind of a weirder example because like we have, well, no, actually it's a good example. If you had X was a matrix, Y matrix, you put it through a function mol, you still get back one intermediate expression. When you do the partial with respect to when you do the partial with respect to V1 here, it's just the adjoint accumulation you care about, right? So it would just be like the matrix. Like, so when you do like the matrix derivative, like that would be the result back. And you'd have different partial derivatives for X and Y still. So you would still have like just one node, if that makes sense.
Any more questions? Jason?
I don't know anything about this topic, and I don't know how well formulated my question is, but I'm curious about memory requirements, sort of for the forward and backward cases. If I have small number of inputs to many outputs, the reverse or similar number of inputs and outputs and I want to use automatic differentiation, will I die in memory usage?
I'd say like, so keep in mind with automatic difference. So in this case, where you're just working on scalars, where normally you just have like a double, you're gonna have that var type that has a value and an adjoint, and then another 8 bytes for like the virtual function. So it's gonna be about 3 times as much memory as you previously had. Does that answer your question?
Yeah. I guess maybe I'm wondering of cases where you have many inputs and many outputs, but you're saying maybe a small factor.
Yeah, it's just gonna be like a small factor usually.
Okay.
It's a small factor times the number of intermediate expressions.
Oh, yeah, thank you.
And so something like an iterative solver that is running a loop, 1,000 times, it will be 3 times 1,000 that loop bodies. So it can, this is often the thing that actually bottlenecks, for example, Stan in practice, is that the number of intermediate expressions gets very, very large and you run out of memory before you'd run out of compute.
So what about like a matrix multiply, right? Where, how do I think about, should I just think that's an enormous number of intermediate operations, or?
Yeah, well, so to cover that part, the reason why a lot of these other packages use this var matrix type is just because it collapses the expression nodes down and saves memory and computation time.
Okay.
Where like, yeah, if you think about doing matrix multiplication with this type here, where you're just doing the simple for loop, like it's going to be super expensive, right? Like you build a bunch of tiny little intermediate expressions throughout this, kind of like going into your question.
I mean, I guess to kind of follow up on Jason's question too, you were saying that if we have many inputs and one output, we should do reverse mode.
Yeah.
If we have one input and many outputs, we should do forward mode.
Yeah.
If we have many inputs and many outputs, does it not matter?
Generally, it's just going to be you will just do whichever. If you have more inputs than outputs, you'll do reverse mode. If you have more outputs than inputs, you'll do forward mode.
And if they're the same, you can do
Yeah,
either.
it's kind of tomato. Right.
If I can comment, so if it's about the same, the forward mode has a little bit less overhead than reverse mode. And in fact, in terms of those memory requirements, so when you're doing forward mode, you're computing the derivatives as you go. So you actually don't need to store the intermediate values because you don't have a reverse path that you need to do afterward. So in that case, forward mode actually does have an advantage.
Okay.
There's other pieces of that too, right? Where like usually reverse mode is often like very well optimized relative to forward mode. So like there's times where we found forward mode to be much faster in Stan Math in cases where we would expect. So there's times where reverse mode was much faster in Stan Math. We would expect forward mode to have been faster. So I guess in that case, I would say test it.
Okay.
As examples. Cool. But yeah, thank you, Charles.
Yeah, missed the first 5 minutes, so you may have described this, but the subset assignment. So do you mean this if I like pass like an array through a differential operation and I ask for the derivative of just one of its inputs without doing the whole, like getting it for the whole array or something like this? Or
So you can do subset. So by subset assignment, I mean I have a vector here that I'm making that's like size 5. I have a matrix that's a 5 by 5, and I want to assign that vector to like one column of that matrix. A lot of stuff just doesn't allow that, which is just a thing that I'm very used to doing in Python and R. So like I usually don't. It's the reason is because like you have to make a hard copy essentially every time they think you need to make a hard copy every time you do it. And so in Stan math, we actually figured out a way to do this very fast. That is still nice and allows for matrix subsets. But essentially that's the thing. Like when PyTorch and JAX were doing this, they didn't want to like paying that cost of like having to make a full copy is very expensive. So they just said, no, we're not going to have matrix subset assignment. But what you're talking about where you just take a slice, that's totally fine. As long as you're just viewing it.
Okay, I think we'll end it there. We can attack Steve with more questions during lunch, which starts right now. So we're back at 2 p.m. With Brian.